Hello friends, welcome back to another video. In this video I want to derive the table of Laplace transforms, and maybe we won't be able to do all of them, but we will definitely do some of them. And the one I've circled here, 37, is the one we're going to start with, because this one actually gives us a lot for free. Okay, so let's see why that happens. So 37. Maybe I will forget to keep numbering them, but this one I'll number. So the Laplace transform of the nth derivative at s is the integral from 0 to infinity. Now here I will write d by dt, and then fn minus 1 of t, e to the minus st dt. You see how that works, right? The d by dt gives us another 1, and that's how we get the nth derivative. And now if I do integration by parts, we can see that the dt's will just cancel. And so the first term will be the boundary term, e to the minus st times fn minus 1t from 0 to infinity, and then minus, and we need to do the derivative on e to the minus st, so that gives us plus s integral 0 to infinity f of n minus 1 t e to the minus st dt. Okay, now this guy, sorry, maybe like this. This is just equal to the Laplace transform of fn minus 1. Okay, so we will have recursion. And this guy, first of all, at infinity, it's 0 because e to the minus st kills it. So we are taking s to be real part positive, obviously. That's why we can kill it at infinity. And so we're only left with the part at 0, so that will be minus fn minus 1 at 0. Okay. Now you see what's going on here, right? Maybe I will just call this L. Oh no, there's no reason to call it anything. So we have the LFN, I'll suppress S, is equal to S LFN minus 1 minus Fn minus 1, n minus 1 at 0. This part here is just a constant, right? And this is a recursive equation. So obviously I could just like copy paste it like this and set n to equal n minus 1. So I just need to adjust, and I can keep going like this until I reach LF at well, 1, right, which would be LF prime, is SLF minus F at 0. Okay, so this final formula is clearly 35. So they use capital F of S, right? So this would be capital F of S. I'm not going to use that. I'm going to write always LFS. Okay, so just LF of S. So just LF of S. Okay. And here we have a big ass recursive formula, so we can just keep iterating it and get what LF of n is. So LF of n, it would just be, so how many times will we have s being multiplied? If it's LF second, we'll have s squared. If it's LF third or triple prime, it will have s to the third. So clearly it'll be s to the n LF and minus s n minus 1 f. Yeah, it should be just f of 0, and then minus sn minus 2 f prime of 0 minus So now there's no s, and it's f and minus 1 at 0. Let's just make sure that's correct. So indeed, that is correct. If it was too fast, feel free to plug in. You could also do this. Actually, yeah, you could do this with matrices, and then you could just invert the matrix to check what this is. That would be kind of interesting. Okay, so there we go. This is 37. Yep. And from 37, we obviously get 35, 36. Maybe I don't need to put, yeah. That's an ampersand, by the way. Okay, so 37 gives us 35 and 36. Cool. Okay, now we can start from the beginning now. And the reason why I wanted to do this one was because, well, pretty much many of them follow from it. Okay, so number 1 is just a constant, right? And then number 3 is t to the n, and number 4 t to the p. So I think we can start with number 4. So number 4 gives what we have: the Laplace transform of t to the p, where p is greater than minus 1. So we set p greater than minus 1 and f of t equals t to the p. Then we say that the Laplace transform of f at s is equal to the integral from 0 to infinity t to the p e to the minus st. So we have to get the gamma function. Let's just write what the gamma function is. So gamma of p would be 0 to infinity t, I believe it's t to the p minus 1. Could be p plus 1. I always forget this. So let's just adjust. Let's say p plus 1 is p. Does that match? Yep, that matches. Okay, I'm sorry to have to match like this, but the gamma function, who's going to remember if it's p plus 1 or p minus 1? And then it's like this. Okay, so it's t to the p e to the minus t. So the difference obviously being the s, we have to get rid of the s. And so here I just wonder how the heck they get rid of the s. They get rid of the s. So 0 to infinity t to the p e to the minus st dt. And here it's t to the p e to the minus t dt. I suppose the s will just come out by itself, yes. So obviously we'll do a substitution here. I'll say that, maybe here I'll change to x. And here I'll say let st equal x, and dt is 1 over s x dx. Okay, 0 infinity doesn't change. So we have 0 to infinity x to the p over s to the p, and then e to the minus x dx over s. So here s p plus 1. Okay, and the thing above is the gamma function. So this is g of gamma, gamma of p plus 1 s over p plus 1. Is that good? Yeah, that's good. Cool. And p is greater than minus 1. Awesome. P is greater than minus 1. If p is equal to minus 1, then you get the, what's it called? The exponential integral or something. Okay. So if p is equal to, so let p equal 0, right? Then we have the Laplace transform of S is equal to gamma 1, right, over S, gamma of 1 over S, and gamma of 1 is just 0 factorial over S. So yeah, if P is an integer, which here it's not necessarily, then this is equal to P factorial. And the way you can see that is when you integrate this by parts, P times, then you'll just have 0 to infinity e to the minus x. But because of the integration by parts, you'll get P times P minus 1 times P minus 2, blah, blah, blah. So that's why the P factorial pops out. So it's much easier to remember this equality than it is to remember this equality. And you'd kind of wish that mathematicians would have called this gamma of P, but unfortunately they didn't, and I don't know why. Okay, so this is 0 factorial over S, and 0 factorial is 1, so this is 1 over S. So this gives us 1, right? So this gives us property 1. Maybe if I'm writing properties, I should circle them. Yeah, instead of the dot. So 37 gives 35 and 36. And here's 37. So, yeah, okay. So that was number 1. We can also get number 5 the same way. But for this, you need to know the value of the gamma function at the particular point. You also obviously get 3 for free. 3 is very easy to get. So yeah, we can get 3. Let P equal n integer, then LF of S is gamma of n plus 1 over S to the n plus 1, and that's n factorial over Sn plus 1, right? Okay, yeah, that's exactly correct. So yeah, that's cool. So 5 and 6 follow from 4. We're not going to do these because for this you need to know the values of the gamma function, or you need to calculate these. There's no point in doing that. So what do we have? We have 7, 8, 9, 10. 7, 8, 9, 10. Well, if we do 7, then from that we get 8 by differentiation. Also 9, if you differentiate it, it gives you 7 plus 10. So probably we should do 9, maybe. Yeah. So is there a condition on this A? No conditions on A. E to the AT sine BT. We could also just do it for 23, and then the rest would follow. I think we can do it for 23 then. So 23, we have f of t is equal to t to the n e a t. Is that correct? T to the n e a t. Yeah. Now, I mean, they don't write anything, but obviously you can't really do this integral if a has real part greater than 0. So I will write real part of a less than 0, less than or equal to. But yeah, technically, this is why you would analyze the stability. So technically these integrals are only formal, and then you would have an instability if the real part of a is greater than 0. But I will keep it like this just to be at least a little bit rigorous. So LF of S will just be the integral from 0 to infinity t to the n e to the s minus a, like this, t dt. And this is clearly just the Laplace transform okay, so now I'm going to write it. Laplace transform of t to the n of s minus a. Okay, so this really isn't difficult at all. This just gives us n factorial s minus a to the n plus 1. All I did was notice that this exponential goes in, and just generally, if you have here g of t, right? Let's write that. Let's write that even more general. So if f of t is g of t e to the at, then the Laplace transform of f at s is equal to the Laplace transform of g at s minus a. This is, it's pretty obvious. And I suppose from this, we can really get all of the sine and cosines. So for example, I don't remember which number the sine was, but sine of at is, of course, e to the iat minus e to the minus iat over 2I. And so the Laplace transform of sine at, maybe let's do t sine at, is at s, is just 1 over 2I. The Laplace transform is linear because integration is linear. So 1 over 2I. The Laplace transform of t, okay, I'm kind of going back on my notation, but okay. The Laplace transform of t, let's write it like that. The Laplace transform at t at s minus ia plus, minus, the Laplace transform at t of t at s plus ia. Cool. Okay, and we know both of these, so we just calculated that in number 4. So this would be 1 factorial over s minus ia. Is it going to be squared? Yeah, it's going to be squared. S minus ia squared minus s plus ia squared. 1 factorial. Okay, and now we just have to expand, find a common factor, and the common factor is s squared plus a squared squared. And above we have s plus ia squared minus s minus ia squared. And I wonder what's going to happen. We're going to have s squared plus minus a squared yep, over 2I, and there's 2 of these guys. S squared plus a squared squared. So we can get rid of the 2, maybe put a minus I here. Get rid of the 2. Is that what you get? That's really ugly. Let's see if that can simplify. So sine, this is this one. T sine at. So 2as. Because there's minus. Yeah, sorry. I was wrong. Because it's minus. Let's be careful. So I canceled the wrong things. So you do get s squared plus 2ias minus a squared, and then minus s squared plus 2is plus a squared, and okay, and that's equal to, so this cancels with this cancels with this, you get 4is, you divide by 2I, you get 2as over s squared plus a squared squared. Okay, that's good, right? Sorry, this takes so long to scroll now. We have a lot of stuff. So 2as over s squared plus a squared squared. That's good. Okay, So let me show you how you get the cosine from here. So then L t cos t, well, it's equal to, so t cos t is t sine t prime, right? Because you get t cos t. And then you also get sine t, so you have to subtract sine t. And sine t we know, I guess we don't know sine t yet. Okay, so we should find t sine, we should just find sine t. So L sine t is of s. Yeah, sorry about that, of s. So L sine t of s would be we'll have 1 over 2i, the Laplace transform of 1 at s. Oh, this is just sine t. Did I have? Yeah, I had sine at here. Okay, let's use at. So then I have to be careful with the derivatives. So sine at prime, and when I take the derivative and get cosine, I'll get an extra a, so I need 1 over a. And then the sine t, so the sine t also has a 1 over a. Okay. So sine t over a, you would get sine at over a plus t cos at. Yeah, that's good. Okay, let's just find the Laplace transform of sine t. So that would be the Laplace transform of 1 at s minus ia plus the Laplace transform of 1 at s plus ia. Just make these square brackets. And the Laplace transform of 1 is just 1 over s. So that's 1 over 2i. So this is 1 over s minus a minus 1 over s plus a, ia. And we expand this, we get 2i s squared plus a squared. And so above we have s plus a, then minus minus s minus a, so we get 2ia, so that's a. Okay, good. That matches. I know this one by heart, so this one's fine. And now, so we've got L of sine t, we've got L of t sine t, so then L of t cos at. Yeah, of course this was sine at. Sorry about that. I mean, you see that the calculation was for at. I just forgot to write the a. Okay. Sine at over a. Yeah, that's good. So the Laplace transform of t cos at would then be. So we're gonna have to use the formula for differentiation. Well, this is interesting, but I guess it's interesting, but I don't know if it would be faster necessarily. I mean, obviously you should just use the table. So the Laplace transform, we have 1 over a, the Laplace transform of t sine at prime, and then minus 1 over a, the Laplace transform, what am I doing? The Laplace transform of sine at, this should be at s. You see, this is why it's important to write at s, because sometimes it's at s minus a, and so on. So the Laplace transform of sine at s, okay? And so the first one, we need to use the derivative property, which is 34, right? So it would be 1 over a, the Laplace transform of the original times s, so we'll write s, the Laplace transform of the original, t sine at s, and then minus at 0, but at 0, luckily. So we forget about the 0. And then minus 1 over a, I'll put that in, so it's a s squared plus a squared. Okay, I put this guy in. And then the Laplace transform of t sine at s is 2as, so 2as, the a will cancel, so 2s squared over s squared plus a squared squared. And then minus, here the a will cancel and I will expand, so minus s squared plus a squared, s squared plus a squared squared. And indeed, what do you mean indeed? We're missing a 2. Are we missing a 2? Because that's 2as. We are, is it 2as? Yeah, it is 2as. Are we missing a 2? Oh no, for t, yeah, I don't know what t cosine t is. We'd be missing a 2 if it were just cosine. So yeah, okay, let's not jump to any conclusions. It would be s squared minus a squared, s squared plus a squared squared. Let's see what t cosine t gives us. So t cosine t, yay, we did it. It is s squared minus a squared, s squared plus a squared squared. Okay, so pretty much the only ones left now would be cosh and sinh, and I'm not going to do this one explicitly, but I will just say that cosh at is equal to cos, maybe like this, cosh iat is equal to cos at, okay. And then sinh, well, let's see, I have to differentiate because I never remember. This one is easy to remember, but let's do by d by dt. So then sinh iat is 1 over I, I'm dividing, right? And then this is minus cosine, so that's, okay, wait, let's go slower. So this is ia sinh iat. This is equal to sine a sine at with a minus. Okay, so the a's cancel, and then dividing by I gives minus I, so this minus cancels, so like this. Okay, so so you just use this substitution. So then if you know that the Laplace transform, okay, so I guess I will do it. If you know that the Laplace transform of sine at s is a over s squared plus a squared, right? That's correct, yeah. Then the Laplace transform of sinh at s will just be, so what do? You replace a by minus ia. You see what I mean? So you replace a by minus ia, and you would get minus ia s squared minus a squared. That should either be good, or maybe I mixed up a minus sign. So sinh at, it's just a over, sorry, I forgot the I here. Yeah. I forgot this I. So I times minus ia, yeah, and then that's a over s squared minus a squared. Yeah. So this is basically how you do it. This I will make sure that nothing screws up, and for cosine it will also be like this. Just s over s squared minus a squared for cosh. Okay, that's it. Sorry, this was way longer than I thought it would be. But we did manage to get through almost the whole Laplace transform table. So there was one that I found interesting that we didn't get to. And that was this one, number 34. Ah, shit. I think I called something 34 when I shouldn't have, right? But yeah, okay. Number 34 is the one that I'm kind of interested in, but I don't want to do it now. Okay, thanks for watching, guys. See you next time. Bye-bye.